We all know AI is completely changing our world, right? But it's got this massive, kind of invisible cost: energy. Today, we're going to dive into a research paper that points to a potential revolution in AI, one that could make it thousands of times more efficient. Seriously.
So, to really get why this is such a big deal, let's start with a number that is just staggering. Projections say that by 2030, AI data centers could be eating up a full 10% of all energy produced in the United States. That is an absolutely insane strain on our infrastructure. And you know what? It's growing every single day.
And it's not just about the power grid. It's about cash. Cold, hard cash. This quote from the paper just floored me. Every single year, the investment in AI data centers is more than the entire cost of the Apollo program to put a man on the moon. Think about that. We are making this monumental bet on the way AI works today. But what if it's the wrong bet? Okay, so where is all this incredible cost coming from? Well, the paper argues it's a direct result of the hardware we've ended up with, a choice that might have just been a complete accident of history.
This brings us to a really cool idea from the paper called the hardware lottery. See, the AI algorithms we use now, like the big large language models, they were all designed to run on GPUs. But GPUs, they were built for video games, for graphics, not for thinking. It was almost an accident that they turned out to be good at it. And because they were, we got locked into a system that might be fundamentally inefficient for genuine AI.
And that leads to a really fascinating question, doesn't it? What if we could just hit the reset button? What if we could build computers from the ground up, tailor-made for a totally different, maybe more brain-like way of processing information? Well, that's exactly what these researchers decided to explore. You know, for a long time, there's been this other really promising alternative to today's AI models. They're called energy-based models, or EBMs. They think about problems in this really intuitive way, but they've always had this one fatal flaw that's kept them stuck on the sidelines.
Okay, so imagine a giant, rugged landscape. The way EBMs learn is by shaping this landscape. The deep, easy-to-get-to valleys represent common patterns, like the features of a cat. The tall, spiky mountains represent unlikely patterns, like just a screen full of random static. So to generate a new cat picture, the model just has to find its way down into one of those cat valleys. Sounds simple, right? Well, not so fast. Here's the catch, and you can see it right here. The better the EBM gets, the more it understands complex, real-world stuff, the more ridiculously rugged that energy landscape becomes. We're talking huge mountains, super deep and isolated valleys, and trying to find your way through that landscape, it becomes exponentially harder. And, as this chart shows, it just eats up a crazy amount of energy. So this right here is the heart of the problem. The paper calls it the mixing expressivity trade-off, or MET. This is the villain of our story. Better performance is literally tied to being harder to compute. It's what's made these really powerful models totally impractical to scale up. Well, until now. And this is where the big breakthrough happens. The researchers came up with a new architecture that just cleverly sidesteps this whole trade-off. Instead of trying to solve one impossibly hard problem, it just solves a whole bunch of easy ones. This new approach is called a denoising thermodynamic model, or DTM, and the core idea is just brilliant in its simplicity. Don't build one massive, complicated, impossible-to-navigate energy landscape. Instead, just chain together a bunch of simple models, where each one has a super easy, gentle landscape. And this just lays it out perfectly. The old way was like trying to climb a sheer cliff face in one go. The new way is like taking a long, winding path made of gentle, easy little steps. Each individual step is simple, but when you chain them all together, you get to the same destination with a tiny fraction of the effort. Let's actually see what this looks like in practice. The whole process starts with just pure random noise, static. Then the first simple model in the chain makes one tiny little change. Then the next one makes another change, and the next one, and so on, each one just gently nudging the noise closer and closer to being something real, until, bam, at the very last step, a clear image emerges. It literally pulls a signal out of the noise. So, okay, we've got this really elegant new software idea, but what does that actually translate to in terms of energy savings, especially if you build hardware specifically for it? Well, the result is, it's just staggering. This is the key question, isn't it? We're not just talking about a new algorithm here. We're talking about a whole new kind of computer built to run it, a probabilistic computer,
one that's designed to handle uncertainty. So what happens when you finally pair the right software with the right hardware?
10,000 times. I'm not making that up. The analysis in the paper shows that a device built on this new architecture could get the same performance as a GPU using roughly 10,000 times less energy. Let that sink in. This chart, which is based on a figure from the paper, just makes it crystal clear. Look at the bar for the GPU system. It's huge. The energy needed is massive. Now look for the bar for the new probabilistic computer. It's so small you can barely even see it on the same scale. It's a total game changer. Now, does this mean we're about to throw all our GPUs in the recycling bin? No, not at all. Instead, the paper points to a much more interesting future, one where different kinds of computers actually work together. The big idea here is to create hybrid systems. You'd use the traditional computers, like GPUs, for the stuff they're really good at. And then you use these new, super efficient, probabilistic computers for the tasks they excel at. Things like reasoning with uncertainty and generating new ideas. It's all about using the best tool for the job. And hey, this isn't just some theory. The researchers actually built a proof of concept. So a small neural network would get the data ready, then the new DTM would do the really hard work of generating something new, and then a decoder would translate it back into an image. And the result? It matched the performance of a traditional AI model, but its neural network part was 10 times smaller. It works. So this all leaves us with a final, really fascinating thought. For decades, the whole goal in computing has been speed, just making our machines faster and more powerful. But this new research suggests a totally different path. What happens when we stop focusing only on making computers faster and we start focusing on making them fundamentally wiser and way more efficient in how they actually think?